In this video, we are going to talk about the intersection of three planes. In talking about the intersection of three planes, we'll be talking about three equations with three unknowns. Recall from earlier that when discussing systems of equations, we can talk about consistent and inconsistent systems. A consistent system is a system of equations with at least one solution that satisfies each equation. In the case of the intersection of three planes, this means that there's at least one point of intersection. We will see that three planes can intersect at a single point along a line of intersection or at the whole plane of intersection. Consistent systems look like what you see on the board there. Case one is a case where all three planes intersect at a point. In case 2A and in case 2B, we have situations where three planes intersect along a line. In case 2A, the three planes are all non-coincident. None of them are the same, but they happen to intersect along the same line. In case 2B, two of the planes are coincident. In other words, two of the planes are identical, and the third plane just happens to not be parallel to it, so it intersects along a line of intersection. There's another case where all three planes are coincident, in other words, identical, and obviously in that case there's a plane of intersection. Okay? Now, an inconsistent system is a system of equations in which there's no one solution that satisfies each equation. In the case of the intersection of three planes, this means there is no one point of intersection. There's no point of intersection. Well, this could happen a few different ways. In one way, none of the planes would be parallel to each other, but they would all have the line of intersection of plane 1 and plane 2, and the line of intersection of plane 1 and plane 3, and the line of intersection of plane 2 and plane 3 would themselves be parallel, even though none of the planes are parallel to each other. And that would indicate a triangular prism, and in that case there would be no point on all three planes. There's another case where two planes are parallel and not coincident, and a third plane is non-parallel, so it intersects them, and the two lines of intersection, the line of intersection between plane 1 and plane 3, and the line of intersection between plane 2 and plane 3 are actually parallel to each other, but there's no point on both those lines. There's no point on all three planes. In another case, we have three planes that are all parallel, but none of them are coincident. And in the fourth case, we have two planes that are parallel and coincident, and so they share all the points in common. And then there's a third plane that's parallel but not coincident, and there's no point that's on plane 3 that's also on both plane 1 and 2. And so therefore, there's no point on all three planes. It's an inconsistent system. Okay. So steps to determine which of the 8 scenarios we have given a certain case. We're going to convert each of the planes to Cartesian form if necessary, and we're going to determine whether any of the normals are parallel. If none of the normal vectors are parallel, then we have either one point of intersection, or three non-parallel planes that intersect along a line, or a triangular prism with 0 points of intersection. We then build a matrix and solve to determine which scenario we have. Okay, so these are the three cases that you can have if none of the normal vectors are parallel. Okay, if you get a single point of intersection, you have the first scenario pictured. If you get a final row of 0, 0, 0, 0, then we have infinite points of intersection, and we must be dealing with the second scenario listed because a line of intersection has infinite points. And point 7 there is if we get a final row of 0, 0, 0, non-zero, then we'll have 0 points of intersection and we'll have the third scenario shown. See, if you have 0, 0, 0, 0 in the last row, basically what you can do is eliminate that row from consideration, and now you've got two rows in your matrix, which basically means you've got two planes and you're looking for the line of intersection between them. But in point 7 there, where it's 0, 0, 0, non-zero, What that would mean would be that, let's say the non-zero number is any random non-zero number, let's say 7. If you had 0x plus 0y plus 0z equals 7, that's impossible. So that would mean that there's no point that satisfies all of them. And if they're three non-parallel planes, it would have to be the third diagram. Okay, now another case, once you have all the normal vectors, another case is that two of them are parallel and the third one's not. If that's the case, then we either have two parallel coincident planes and then a third non-parallel plane, so there's a line of intersection like in the first diagram, or we have two parallel non-coincident planes, so there's no points of intersection between them, a third non-parallel plane, so it intersects at lines of intersection, and we have the second diagram, and it's an inconsistent system because there's no point on all three. The first diagram is a consistent system. The second diagram is an inconsistent system. Now, if the two planes are parallel and non-coincident, then the third, again, we're just describing the second diagram. The system's inconsistent. Okay, now, what if we have three normal vectors that are all parallel to each other? Well, the easiest case would be if all three of the planes were coincident. That's the first diagram, infinite points of intersection, and therefore it's a consistent system. The second diagram is where two planes are parallel and coincident. The third one's parallel and non-coincident. There's no point on all three planes, inconsistent system. And finally, in the last diagram, you have three parallel non-coincident planes, and so there's no point on all three of them. Okay, so let's go about this. We're going to end up doing one of each of those scenarios. What if we wanted to solve the following system of equations? Well, what we're going to do is we're going to convert it to Cartesian form, which in this case basically just means we're going to move all the terms to the other side, the constant terms to the other side. It allows us to augment our matrix. So we have that. That's pretty straightforward. Now look at our first normal. Our first normal vector, looking at the A, B, and C components, is 1, 1, negative 3. The second is 5, negative 4, 2. And the third is 2, 3, negative 1. Well, none of those are parallel. So that means we're going to do matrix work. Okay, so we set up our matrix, and we're going to do some elementary row operations. Perhaps we can multiply the first row by 10, the second row by 2, and the third row by 5, and that'll give us tens in that first column. We can then subtract row 1 minus row 2 and row 1 minus row 3. So when we do that, we have what you see shown here. Now, we're now going to see if we can get these two the same. And we can do that if we multiply row 2 by 5 and row 3 by 18. If we do that, we end up with a 90 and a negative 90. We now know that we can add row 2 and row 3. The zeros won't have any effect on each other, but the 90s, when you add them, they'll cancel each other out, the 90 and the negative 90. And when we do that, we get what you see here. Now, a lot of times I'm looking to get a triangle of zeros in this place here. It doesn't have to be specifically there, but I'm looking to get a triangle of zeros. So what we did is we first got all the coefficients in that first column to be the same, and then we got the once we did that, we did some subtraction, and we got a couple of zeros here. We got these to then be the same, and we added. One was positive, one was negative, and we got a triangle of zeros. Now, what's the benefit of that? Simple. We can now say negative 620z equals negative 3,720, meaning z is 6. Well, if z is 6, we can take that value and plug it into that equation in the second row. And when we do that, we get y equal to negative 3. And we can then take that and plug it into the first row. And when we do that, we get x is equal to negative 2. And so what we have is that the solution of the system is -2, -3, 6. And so we have three planes intersecting at a single point. Now, what if we have the system of equations shown there? Okay, well, pretty straightforward. Normal 1, normal 2, and normal 3. As shown, none of those are parallel to each other, so we're going to have to build a matrix and solve it. So we do that. Hopefully that's relatively straightforward for you. And now, ordinarily at this point, we try to eliminate the x component of the last two rows. However, we don't always have to do that. In this case, notice we already have a 0 here. Look at that, it's right there for us. And not only that, but we actually have a 10 and a 10. So it's going to be pretty easy for us to do some subtraction, row 1 minus row 3, and have a couple zeros in the Z column. So we'll try that this time. However, if we didn't like doing that and we were really comfortable with always eliminating the terms in the X column, we could do that. We could simply multiply the second row by 3 and the third row by 3 and then eliminate that X column. But what we're going to do, we're going to focus on the Z column here, just to show you it doesn't always have to be done only one way. So we already have the 0 where we wanted it there, so we're not going to do anything. But here we're going to subtract 10 minus 10, and that's going to give us a 0. But if we do that subtraction, we have to also subtract -4 minus -8, which gives us a 4. We have to subtract 3 minus 1, which gives us a 2. And -22 minus -54, which gives us 32. And so we have the three rows that you see there. Now, what we're going to do is we're going to say, you know what, we can multiply this row here by 1/2. Or, you know, if we wanted to, we could have multiplied that row there by 2. But we're going to multiply the last row by 1/2. And when we do that, we're going to see here, between row 2 and row 3, we're going to see an opportunity to eliminate. We're going to subtract 1 minus 1, and we'll get 0. And then we're going to subtract 2 minus 2, and we're going to get 0. And we're going to subtract 0 minus 0, we'll get 0. And we're going to subtract 16 minus 16, and we'll get 0. So what we have there in that bottom row, some people like to look for a triangle of zeros. It doesn't have to be a triangle, but you know, in this case, we can make that if we like. But it's kind of, that's okay, but notice that the last row is all zeros. 0x plus 0y plus 0z equals 0, that's not really helping us at all. We already knew that. That's true no matter what the numbers are. So we can kind of eliminate this from consideration. Once we've eliminated that from consideration, then look what we really just have. Two rows, two equations with three unknowns. And so we're going to get an infinite number of solutions. Okay? So looking at the last row, we have x plus 2y equals 16. Since we have two equations with three unknowns, we're going to have to assign a value to one of the unknowns. So let's either assign a value to x or to y, and then we'll be able to get one possible solution. So we're going to let x equal 0. We know from the last row that x plus 2y plus 0z equals 16. Let's let x equal 0. We're just giving either x or y a random value. Once we've chosen x equals 0, then that means 0 plus 2y equals 16, which means y equals 8. So what we're doing is we're building one random solution, and it has an x value of 0, a y value of 8, and so far an unknown z value. Well, we should find out what that z value is. And why are we doing this? We're doing this so we can have one point that's on all three. But you might have thought to yourself, wait a second, what we've got here is two planes that we're basically looking for the intersection of, and they're not parallel, so there must be a line of intersection. So we're really looking for a line of intersection, and what we're doing at first is finding a point on that line. As soon as you find a point on that line, you can use the values, the coordinates of those x, y, and z of that point, and you can call them the components x, y, and z of the position vector on the line of intersection. We'll be able to get a vector equation of that plane. That's our strategy. So anyway, so far we know that there's a point on the line of intersection that has an x coordinate of 0, a y coordinate of 8, and an unknown z coordinate. How are we going to figure out that unknown z coordinate? Easy, by using the first equation. 3x minus 4y plus 10z equals negative 22. Okay? So once you plug in an x value of 0 and a y value of 8, you can solve for z. Z ends up equaling 1. So what that means is the point 081 is a point on the line of intersection. That means the vector 081 can be the position vector of our line of intersection in our line written in vector equation form. Okay? Now, how are we going to get the direction vector? Well, it's actually pretty simple. All you really have to do, if you know that these three equations, we know that we've got three non-parallel three non-parallel planes intersecting along a line of intersection. What we can do is take the normal vector of any two of them, cross them. That'll give us a vector perpendicular to both of them, but it'll actually be parallel to the line of intersection. So that's cool. So we'll just pick we could have determined the cross product of normal 1 and normal 3, or normal 2 and normal 3. We'll find the cross product of normal 1 and normal 2. Finding that cross product we see is negative 20, 10, 10. But since we're using it as a direction vector, we can actually multiply that by a scalar to simplify it. So multiplying negative 20, 10, 10 by negative 1 over 10 gives us 2, negative 1, negative 1. And that vector right there has the advantage of having a positive lead component and also reduced values. Okay, so we now know a point, which was 081, so we'll use 081 as a position vector, and we have a direction vector of that line of intersection too. All right, let's do a third example here. We're going to solve this system of equations. The first normal, second normal, and third normal are written there. None of them are parallel, so that means we have to construct a matrix. Okay, so we construct that matrix, and we're going to get our Z column to all have a magnitude of 10. We do that by multiplying the first row by 10, the second row by 2, and the third row by 5. Now they're all 10s there. Now what we're going to do is simply, we're going to add, first what we're going to do, we're going to add row 1 and row 2. We'll get the row you see there. Then we're going to add row 1 and row 3. We get the row you see there. And at this point, there's no harm in writing 40, 20, negative 10, 120 as the first line. But we can make our lives a little bit easier by reducing that. Let's multiply it by 1/10. And so we have 4, 2, negative 1, 12. Now what we're going to do is see that we can multiply this first row. Our numbers are going to get pretty big if we try to make 14 and 45 have the same value, or 42 and 135 have the same value. Our numbers will get big. So and there's nothing wrong with that. You'll get the right answer, but trying to be a good influence on you here. If you use a little number sense, you realize in your second row, all those numbers are divisible by 2. And in your third row, all those numbers are divisible by 15. And so if you want, you can actually multiply row 2 by 1/2, row 3 by 1/15. And you have basically the same equations, but they're a little bit simpler to now try and make those, pick a column and make those values the same. So what we're going to do is we're going to get a couple of 21s here. So we'll multiply row 2 by 3 and multiply row 3 by 7. And when we do that, we get the values you see written in that most recent matrix. We do our subtraction. We're going to go row 2 minus row 3. 63 minus 63 is 0. 21 minus 21 is 0. 0 minus 0 is 0. And 213 minus 72 is 141. We have our triangle of zeros, if that's something you want to go for. But more significantly, what you have in that last row is an impossibility. This last row is saying 0x plus 0y plus 0z equals 141. That's impossible. There's no way that can possibly happen. So, therefore, there are no points of intersection. So we have three non-parallel planes with no points of intersection. We must have a triangular prism. Now, what if we have the system of equations you see shown here? We're going to now get into situations where instead of having three planes that all have non-parallel normals, we're going to get into a situation where we have some parallel normals. So the three normals written are there, and right away you notice that two of the normals are parallel. Okay, we have 322 as normal 1 and 644 as normal 3. Obviously, those are parallel, and since they're parallel, we know we're not going to have to build a three-row matrix. So if you look at the first row, it's easy to multiply that first row by 2, and we get 6x plus 4y plus 4z equals 44. Well, right away we see that that's exactly row 3. So basically, we can eliminate row 3 because it's exactly the same as row 1. It's two coincident planes. So what we've got here are two coincident planes and a third non-parallel plane that must therefore intersect at a line. After getting rid of that third plane, we basically just have a simple example of two non-parallel planes intersecting along a line, and our job is going to be to figure out an equation of that. So let's multiply row 2 by 3, and when we do that, we get this row that you see here. And we can now subtract 3 minus 3, 2 minus negative 12, 2 minus 18, and 22 minus 45. Okay, and now we get the row you see there. And now what we can do is come up with a value of y and a value of z that satisfy that equation. Because ultimately what we have here are two equations and three unknowns. So we're just going to let y equal 0. And that would mean negative 16z equals negative 23, so z is 23 over 16. So what we have is a line of intersection, and one of the points on that line has an unknown x coordinate, but has a y coordinate of 0 and a z coordinate of 23 over 16. If we can figure out what that x coordinate is, then we can think of these coordinates as components of a position vector on that line of intersection. So we're going to plug in the y value of 0 and z value of 23 over 16 to the top row and simply solve for x. Okay, so doing that, we get x equals 51 over 8. And so we can say that one of the points on the line is 53 over 8, 0, and 23 over 16. Now, I've seen well-meaning students then multiply every one of those numbers by 16 and come up with 102, 0, and 23. We can't do that. We would do that if this was a position, if that was a direction vector, but it's a position vector, so we're not going to. Okay. So to determine the direction vector, all we have to do is get the cross product of the normal vector of plane 1 and plane 2, or if we wanted, we could do plane 3 and plane 2, it doesn't matter. And so we'll get the normal vectors of the first and second plane and get their cross product. Their cross product is 20, negative 16, and negative 14. We can divide each of those by 2, or in other words, multiply that direction vector by a half and get a direction vector of 10, negative 8, negative 7. And so what we then have is an equation given here with our position vector, as stated earlier, and our direction vector of 10, negative 8, negative 7. All right, now what if we have the system of equations shown right there? Well, we've got the normal vectors shown, and as we see, normal 1 and normal 2 are in fact parallel. So the three planes are going to represent an inconsistent system with two parallel non-coincident planes and a third non-parallel plane intersecting each of the other two. Well, how do we know that? Simple. Basically what we're doing, and this is what is written in this paragraph here, That paragraph's kind of the key one. We know that normal 1 and normal 2 are parallel. And we can kind of see by observation, multiply the first normal, all three components, by 3, and you'll get the second one. So let's take it a step further. Let's multiply the whole equation by 3, every term in it. So what we would get if you multiplied the first row by 3, you would get 15x minus 33y plus 51z minus 270 equals 0. But if you notice, the second row says 15x minus 33y plus 51z minus 200 equals 0. Well, it's impossible for something to satisfy both of those. To put a little bit more of a fine point on it, imagine that you move this negative 270 and negative 200 to the other side. So imagine you had 15x minus 33y plus 51z equals 270. Well, if that's true, it can't possibly be true that 15x minus 33y plus 51z equals 200. You can't have both. So since it's impossible for a point to satisfy both equation 1 and equation 2, we have an inconsistent system. But since two of the planes are parallel quite evidently, we can make the statement in red. The three planes represent an inconsistent system with two parallel non-coincident planes and a third non-parallel plane that intersects each of the other two planes. Now, what if we have the system of equations shown here? Well, we see, believe it or not, that we have all three normals parallel. So what we can do is say, well, let's check out the d values. We know that that first line is 2x minus 9y plus 4z equals 15. We know the second one is 4x minus 18y plus 8z equals 30. And we know that the third one is 8x minus 36y plus 16z equals 60. Okay, fair enough. What we're going to do is we're going to multiply that first row here, that first one, multiply it by 4. If you do that, you get 8x minus 36y plus 16z equals 60. Multiply that second one by 2, and you get the exact same thing. 8x minus 36y plus 16z equals 60. And then that fourth row, the third row, just leave it alone. This third equation. And so basically what we're saying is every single one of those equations is identical. So we have the exact same plane written 3 times. It's obviously a coincident plane, a coincident system. And so, I'll say that again. It's obviously a consistent system. Every point is on all 3 of them. So we have 3 coincident planes, a consistent system. Now, what if we have the system shown here? Well, in this case, we certainly have 3 parallel planes. If we take it a step further, we can multiply that first row by 2. We'll get 10x minus 2y minus 2z minus 30 equals 0. That second one, we can multiply it by 1, leave it alone, and we have the exact same equation. So obviously what's happening is the first 2 planes are actually identical. So for purposes of our analysis, we can just sort of ignore that plane just for a moment. Remember that it's identical to the first one, in other words, consistent, and now consider the third one. Well, if we take that first plane and multiply it by 3 instead of multiplying it by 2, you'd have 15x minus 3y minus 3z minus 45 equals 0. Well, that's parallel to, but certainly not coincident with the third one. So basically what we have, that's a long-winded way of me saying, we have 3 parallel planes. 2 of them are coincident, 1 of them is not. Therefore, it's an inconsistent system. So if you understand the sentence written in black there, the paragraph, I should say, all 3 normal vectors are scalar multiples of each other, meaning all 3 planes are parallel. The d values for the first and second plane maintain the multiple, but the d value for the third plane doesn't. If you understand that, then you're fine for this type of question. And finally, this last one, basically, much like the one we just did, we've got the parallel normals, but the one difference is none of the d values actually maintain the scalar multiple. If you were to multiply through and make every single one of those have um, a lead term of 30, you'd have 30x plus 120y minus 120z minus 390 equals 0. If you multiplied the second row by 3, you'd have 30x plus 120y minus 120z minus 120 equals 0. And finally, if you multiplied that last row by 10, you'd have 30x plus 120y minus 120z minus 180 equals 0. And you'd see that we certainly have parallel planes, but none of them are coincident because the d values don't maintain. If you bring them over the equal sign, they won't maintain the multiple. So we definitely have an inconsistent system with three parallel non-coincident planes.